Hello friends, welcome back. So we'll be starting with a second unit or second lecture, which will be the continuation of the last one, fundamentals of digital circuits. So we'll be looking at the Boolean laws and axioms. So let us try to understand what do you mean by axioms, or it may be also called as the postulates of the Boolean algebra, which is nothing but a set of logical expressions that we can accept without any proof, upon which we can build the useful theorems which can be used for developing the combinational circuits or sequential circuits. Okay. So axioms are nothing but more than it's a definition of three basic logical operations: and, or, and not. So let us consider this one. So 0 and with 0 is obviously 0, 0 and with 1. So you can see that this is nothing but a truth table of AND operation, OR operation and NOT operation. So these axioms are without proof, we are accepting it for solving the various theorems that we can set, or various Boolean laws we can set. So these are the Boolean laws we came across in AND form and OR form. So first one is the identity law. So we'll try to prove it. First we'll talk about the first identity law, that is called as this one, 1a into, let us try to do it over here. Let us consider a is equal to 0 and a is equal to 1. Okay. Now 1 dot 0 will be obviously 0 and 1 dot 1 will be obviously equal to 1. So that's why 1 dot a is equal to a. So this is how it can be proved. So similarly 0 plus a is equal to a. Obviously when a is equal to 0, 0 or 0 equal to 0 and 0 or equal 0 or 1 equal to 1, that's why we can say that 0 or a equal to a. So this is how it works. Okay. Similarly null law, anything into a or if you add anything with 0, obviously the output will be 0, and anything you OR with 1, obviously it will be 1. So that will be called as a null law. Then a dot a is equal to a plus a is equal to a, so that is called as the idempotent law. Then inverse law, a inverse a is equal to 0 and a inverse a is equal to 1. So we can prove it with the help of truth table also. So commutative law, a and b is equivalent to b and a plus b is equal to b plus a. So what we can do it with the help of truth table. So just try to prove this commutative law for AND form. So we can do this one. Let us try. This is a, this is b. Okay, so here it is a b and here it is b a. So we will take the example. Let us say this is 1, this is 0, right? So obviously a b is equal to 0 and b a will be also equal to 0. Now let us take both the cases equal to 1. So obviously a b is equal to 1. So b a is also equal to 1 if you go with the truth table of AND. So this is how we can prove this. Okay. Next one is the associative law. A b into c is nothing but, you can take the product of b and c, that is a logical AND of product, and you multiply it with a. So the meaning is same. So commutative law, a plus b plus c is equal to b plus c plus a. It is equivalent. Distributive law, now we will try to prove this one. Let us say this is A, this is B, and this is C. So A plus B plus C, we will write here A plus B C, and we will take A plus B over here and A plus C over here, and let us try to take the multiplication of this as a Y output over here. Okay, now let us consider that this is 0, this is 1, and this is 0. So A is 0 plus B and C is obviously 0. So the output here is equal to 0. Now A plus B is 1 and A plus C is 0. So 1 into 0 is 0. Now let us consider this is 1, this is 0, and this is again 0. Okay. So what will happen to this one? Now this is 1 plus, so this is 0, 0 into 0 is 0, so this is 1. Now let us try with this one. A plus B is 1 and A plus C is again 1, so 1 into 1 is 1. So this is how we can prove a distributive law. So similarly it is also applicable in OR form also. Absorption of A into 1 plus B is equal to A, and A plus AB is equal to A. So we can also prove this one, that is called as the absorption law. And De Morgan's theorem, which is the most important theorem, that is, we can say that this is equal to NAND is, we will call this one as, this is a NAND gate which is equivalent to bubbled OR gate, right? And this is a NOR gate which is equivalent to bubbled AND gate. And we have proven this. You can find it, the proofs, with the help of truth table. So you can prepare a truth table for this one also, and you can check whether this De Morgan's law is proved or not, because most of the times we are using these laws to solve the equations, Boolean equations. The basic function purpose of using these Boolean laws or axioms is to reduce the Boolean equation to the minimum number of variables. So the purpose or the aim of the digital designer should be is that we should reduce the number of variables so that the circuit can be designed, and this is going to affect many parameters like the cost of the circuit, obviously the speed, the propagation delay, and there are many parameters related to that one. So that design should be optimized one, and for that purpose we should use these Boolean laws to reduce the equations. Okay, so this is how we can start with this one. So now your task is to come up with the symbol for XNOR and XNOR gate. We have already seen in our first lecture, that is in part 1, we have already seen that we have to come up, you have to draw the circuit for XOR gate and its equivalent electrical analogy and truth table for that one. So you can work this one with this one. So we'll take a pause over here. Let's try for this one. Okay, hope you might have got 3 options for this one. So XNOR is nothing but XOR followed by a NOR gate. So it is shown by the complement of XOR. So that is nothing but A dot B plus A bar into B bar. So that gives you the XNOR gate. So whenever your output is equal, so XNOR you can use it for equality type of comparison, where the 2 bits are equal, you will get output equal to 1. So here it is the example of XNOR. So you can easily find out the XNOR gate to get the output. Okay, so this is the basic function we have already seen. Okay.